We begin our chapter on area with parallelograms. As you remember from chapter 8, squares, rectangles, and rhombuses are all parallelograms, and so the one formula we have for the area of parallelograms applies to all of them in addition to just plain parallelograms. The formula is quite simple. Area equals base times height. Only a few things do I need to point out here. One is that this side is not the height of the parallelogram. The height of the parallelogram has to be perpendicular to the base. So do not make the mistake of multiplying the length of this side times the length of that side. That will not give you the area of the parallelogram. In any case, the formula is simply base times height, or A equals BH. This is an extremely simple example. In this case, we have a rectangle. And again, we don't have a formula specifically for rectangles, although you might remember base times height from elementary school. But that is the formula they're going with. This is a parallelogram, and so the area equals base times height. The base, depending on how you turn your head, I'm going to say this is the base. It's 7 feet wide, and the height is 6. 7 times 6 is 42. Extremely simple. Again, you did this in grade school. Find the perimeter of parallelogram 5. Okay, this is the perimeter, not the area. And hopefully you'll remember that the perimeter is the distance around a figure. So we're going to simply add the 4 sides. We have 2 sides that are 32, the bottom and the top. And we have, put P for perimeter. And we have 2 sides that are 24, the left side and the right side. Again, I remind you that this side is not the height. Rather, this is the height. Okay, 48 plus 64 is 112, I believe. Very simple. If I got the math wrong, correct me. We have the same parallelogram on this page that we did on the previous one. This time, however, they're not asking for the perimeter, but the area. So we're going to use our area formula. It's base times height. The base is obviously 32 inches. The height is just a little bit more complicated. Again, the height is not 24, as we might look at first glance and think. The secret to finding out the height of this triangle, or I'm sorry, this parallelogram, lies in this triangle right here. We see that it's a 90-degree triangle, and one of the angles is 30. This is a 30, 60, 90 triangle. We have special formulas for that. If you'll remember, the hypotenuse is equal to the short leg times 2. Well, if the hypotenuse is 24, quite obviously the short leg is 12. The height of a parallelogram happens to be the long leg of this 30, 60, 90 triangle, and the long leg is always equal to the short leg times the square root of 3. So I'm now going to plug that in for the height. 320 plus 64, 384 times the square root of 3. This answer is exact. If you were to approximate it, I suppose there's nothing wrong with that. I can't do that in my head, or at least not very quickly, so I'm going to move on. Okay, sometimes they tell us coordinates of a particular quadrilateral or of a parallelogram, and we can find it just by plotting the points. Again, the formula is area equals base times height. And we can simply count off the base. It goes from -5 to +3. So that's a 5 for this part and 3 for this part. So the entire base is 8. The height, again, I'm just going to do a little counting. From 3 to 0 is 3. And then 4 more. That's 7. The area of this parallelogram is 56 square units. We're going to jump right into lesson 11.2, where we learn formulas for triangles, trapezoids, and rhombi, or rhombuses. You might be thinking to yourself, well, rhombuses are parallelograms. I already have a formula. And you do, but we're going to learn another one as well. Okay, triangles, area is 1/2 base times height. So you're familiar with that much, right? You might think to yourself, if you double a triangle, you've got a parallelogram. And so the area of a triangle is half that of a parallelogram. Important points to make here include the base can be any of the 3 sides of the triangle. We typically choose the one that is the bottom, I suppose. And an extremely important important point here is that the height, just like with a parallelogram, the height has to be perpendicular to the base. The only situation in which you have a triangle whose base and height are actually both sides of the triangle would be in the case of a right triangle. But frequently that's not the case. Okay, let's do an example. Find the area of the triangle. Well, the area is 1/2 base times height. In this situation, the base is clearly 6 inches. The height is clearly 4 inches. The area is clearly 12 inches squared. Okay, this problem looks slightly more confusing. We don't have a formula for the area of a general quadrilateral. However, I hope you'll notice that I don't simply have a quadrilateral here. I have two triangles. Okay, and I can figure the areas of these out separately and add them together. The area of the first triangle, the base, they tell us here that GE is 35. That's the base of our triangle. Area is 1/2 the base times the height, which is obviously 18. Now, the area of the lower triangle, 1/2 base times height. Now, clearly there is no bottom side here. I don't know this, I don't know that. But if I turn my head upside down, and you can imagine me doing that, this is going to be the base. Again, it's 35, and the height is 10. Again, it's always crucial that your base and your height are at 90-degree angles from each other. So this is 5 times 35, which is 175. And this first one here is 9 times 35, which is 315. We simply add these two areas together and get the total, 490. 490 units squared. And finally, the trapezoid. This one's actually similar to triangles. 1/2 base times height, if you will. It's actually a couple of, there's 1/2 base times height, 1/2 base times height. Anyway, yeah, so memorize this formula. It's often easily implemented. It says find the area of this trapezoid. Okay, the area equals 1/2, parenthesis, base 1. It doesn't matter which is which. I'll call the first base 8. The second base is 11 times the height, which is 10. So I have 5 times 19, which is 95 square kilometers, a very large area in this situation. Find the area of this trapezoid. Again, just because it's on the coordinate plane doesn't mean it's any scarier. 1/2, I've got two bases. Remember, the bases are always the parallel sides. This base goes from -1 to +4, so it's 5. This base goes from -2 to +6, it's 8. And this base goes from -1 up to 2, so the height is 3. And I'm just plugging this stuff in. 5 plus 8 times 3, 19.5, I believe. Again, square units. Areas measured in square units. And another formula for the rhombus. If you'll notice, because the diagonals of a rhombus are perpendicular, which I'm sure you remember from chapter 8, what I have here is 4 triangles. And anyway, you can kind of rearrange these and you have a couple of rectangles. This is our formula. 1/2 diagonal 1 times diagonal 2. The diagonal 1 here represents the entire length of the diagonal. It's not just this half. It's the entire length. And D2, the second diagonal, is the entire length of that segment as well. So let's do an example. Find the area of the rhombus. Okay, area equals 1/2 the diagonal 1. We'll call this our first diagonal. It's 20 plus 20. It's 40 feet. And our other diagonal would be this guy. 30 plus 30 is 60 feet. And I believe this is 1,200 square feet. Okay, it says rhombus is an area of 64 square meters. Find AY. Notice that AY is one of the diagonals. If XZ equals 8 inches, well, XZ is the other diagonal. So I'm going to start with the same formula. And this time, instead of plugging both the diagonals in to find the area, I'm going to plug in the area. One of the diagonals, they said, we don't know AY yet. So I'm going to look for AY times the other diagonal, which is 8 inches. And I'm just going to do math here. Clean up a little bit. 1/2 times 8 is 4. Divide by 4. So our other diagonal, which is AY, is going to be equal to 16. Okay, trapezoid. As soon as you see trapezoid and area, immediately write down your formula. We've already worked a trapezoid problem. They gave us both the bases and the height. In this situation, they give us the area. So it looks like we're going to be solving for something else. What are the bases? Okay, I'm just going to look at I see that they're 10 and 20, and it's the height that they want to know. Again, I'm just going to do a little bit of math, a little bit of arithmetic. 10 plus 20, I'm doing this first because it's inside the parentheses. 10 plus 20 is 30. Half of 30 is 15. Times the height divided by 15. So the height of this trapezoid has to be 8. All right, we're going to do 2 more quick lessons, all in this one video. We're only doing half of lesson 3 right now because the other half is fairly complicated. The area of a circle, pi r squared. It only depends. The only thing that can change the area of a circle is the radius. Pi is a constant, 2 is a constant, and therefore the only thing that determines the size of a circle is the length of the radius. Straightforward. Find the area of the circle. The formula is pi r squared. Pi. Stand back for a second. Think about what the radius is. If the diameter is 6 inches, then the radius is 3. 3 squared is 9. So this is 9 pi. Your calculator will approximate that for you, but I'm perfectly happy with 9 pi inches squared or squared inches. Okay, lesson 11.4 is kind of a joke. I tell my students that it's only there because they couldn't justify having a whole chapter about 4 lessons. Irregular figures. So no new formulas at all. Simply you chop up the irregular figures into figures that you already know formulas for. So for example, in this situation, on the left side I clearly have a rectangle, and on the right side I have a triangle. So I'm just going to figure out these 2 areas separately. The area of the rectangle is base times height, and the area of the triangle, and you might say to yourself, well, what's the base? You're going to need to turn your head about 90 degrees to the right, and you can see that this will be our base, this will be our base, and this is the height. So the base then is 62 times the height. This is a triangle, so the area is 1/2 times base times height. I can't do this in my head, or at least not quick enough. So you're going to find these 2, add them up, and that'll give you the total answer. Okay. In this situation, we've got a little bit more going on, but still very distinct shapes. So we have a rectangle, we have a triangle, and we have 1, 2 semicircles. The rectangle's area, base times height, is 32, and it's 16 tall. The area of the triangle is going to be 1/2. I'm going to ask you to turn your head upside down, or at least imagine your head all the way upside down, so that this is our base, 32, and this is our height, 15. Area of the base is 32, area of the height is 15. And then finally, these 2 half circles, you could imagine snipping them off and putting them together, and you would actually have 1 circle. So the area of that 1 circle is pi times the radius squared. Well, we can see that the diameter is 16, so the radius is 8. This is 64 pi. If you want the total answer, plug these 3 in and add them up. Sometimes we'll go into the coordinate plane. All we have to do is chop this up. Now, before we do that, I should point out that this is actually a trapezoid. The top and the bottom are parallel to each other, so we could use that formula, or we could just chop it into a triangle and a rectangle. Over here, the area, well, it's base times height. Base is 5, height is 3, so the area of a rectangle is 15. Over here, the area of a triangle is 1/2, the base is 4, the height is 3, so the area over here is 6. 6 and 15, the area of the entire polygon is 21 square units. And last one. This one is a pentagon. We have no formulas for that. It's particularly not an irregular pentagon. And what I'm going to do is slice it up. Okay, you might try cutting like that. The problem is this is not a nice intersection there, so I need to reevaluate this. Uh, okay, notice that if I go from here to there, I've got a triangle in the bottom. Triangles are good, and from this point, I can pull it straight down, and I've got a nice intersection here. One triangle, a trapezoid, and another triangle. Let's see, this base is 3, and counting, I see this height is 5. For this trapezoid, I've got one base is 5, the other base is 2, and the height is 1, 2, 3, 4, 5. And then finally for our triangle down here, if I turn my head upside down, the height is 2, and the entire base is 3 plus 5, the base is 8. So, adding up the parts individually, this triangle, the area is 1/2 times the base times the height. The trapezoid over here, the area is 1/2 base 1 plus base 2 times the height. And the triangle at the bottom, the area is 1/2 times the base times the height. So this is 7.5. This is 7/2 of 35 is 17.5. And this is simply 8. If I add these up, the area of the extremely irregular pentagon is 33 square units.